Assume that you are given a traffic network as the one in the figure. Assume also that you want to know the travel times of different paths in the network when the traffic demands associated with this path, which vary with time, are known. This means that the travel time for any path depends on the daytime and the associated congestion. We have several models in the system literature to solve the static problem, that is, the daily mean travel times, but it is not easy to find dynamic models, that is, models that consider the travel daytime and the congestion changes during the day. However, knowledge of these travel times is important for you to decide when to travel and avoid traffic delays and congestions. This figure shows the city of Cuenca with its main streets. If you have a computer program to analyze the problem described above, you will be able to inform people about travel times and provide some recommendations for people to benefit from this very useful information. So, we are in front of a very important problem. In this video, we want to explain you step by step how to build a model able to solve this problem and how to implement this model in a language such as MATLAB. The aim of this work is to motivate people to use modeling techniques to solve their problems by first understanding the problem, next writing the model in terms of equations, and last writing the MATLAB code to be able to use the model. In this video, we show you how to build a traffic model in which traffic circulates all over a given network, assuming that a set of paths is used. We also show how to write a computer program in MATLAB to implement this model in your computer. So, after a detailed analysis of this video, you will learn what a dynamic model is, its main equations, and how to implement it in real practice. Before modeling a given problem, we need to understand it very well and think about what we want to make with our model. Next, we need to identify all the variables or functions to be relevant to our model. After this process, we have considered to include the following functions. 1. XA of t, which is the number of users on link A at time t, link traffic volume. EPA of t is the accumulated number of users of path P at n of link A at time t. EA of t is the accumulated number of users at n of link A at time t. Rn of t is the accumulated number of users at node n and time t. TA of t is the link travel time for users entering link A at time t. Theta AP of t is the departure time from the origin of path P of a user who exits link A of path P at time t. Tau A of t is the exit time for link A associated with its entering time t. Tau A minus 1 of t is the entry time of a user that exits link A at time t. QA of t is the Q dissipation time at link A at time t. T out of TAK is the link exit time of a user who enters link A at time t of k. And finally, SA of t is the link A congestion ratio. All these functions are again time, user, or dimensionless variables, as indicated as t, u, or 0 respectively. In this transparency, we have the notation used for the data of the problem. They include the function HP of t, or better, the normal cumulative density basic functions f, n of mu and sigma. The total number of users n. The number of users np of path p. The set of links ap of path p. The set of links whose tail node is node n. The set of all links. The number of components of the HPT function. The set of paths PA containing link A. The reference time T0, usually 1 hour or 1 day. The set of discrete times Tk, k equal to 1 to m, to be considered for the spline functions. All these data are time, user, or dimensionless data as indicated as t, u, or 0 respectively. Next, we discuss other notations. We denote t and p to the time and the path respectively. The parameter notation is as follows. xa max is the number of users on link A leading to a travel time alpha A times 1 plus beta A. Mu Ri is the time mean of the ith component of path P. Sigma Ri is the time standard deviation of the ith component of path P. Alpha A is the free flow travel time of link A. Beta A is the link saturation factor of link A. And finally, gamma is the link saturation exponent of the link travel time function. Finally, phi of n of mu and sigma of t is the probability density function PDF of the normal distribution with mean, mu and standard deviation sigma. When modeling, it is very important to use dimensionless models, that is, models based on the Buckingham theorem, which allows us A. to reduce the number of variables without losing generality, and B. to work with dimensionless variables or functions. Since we have only time and users dimensions, we can choose the reference time t0 and the total number of users n as normalizing variables. That is, we divide by t0 or n all variables, depending on their dimensions, and get the corresponding dimensionless variables, which are two less in number. This justifies the proposed model under a dimensional analysis point of view. To make things easy, we use the simple network in this figure, which contains 6 nodes and 9 links together with the allowed flow directions by means of arrows. In the table, we define 9 paths which have been partitioned into 3 OD origin-destination pairs. There are 3 origins, nodes 1, 2 and 3, and only one destination node, which is node 4. The paths are defined using the associated links. For example, path 1, which is one of the 1-4 of the pair, contains links 1, 5 and 8, and path 8, which is one of the 3-4 of the pairs, contains links 7, 6 and 8. All the paths have been highlighted in red in the right part of the figure, where you can see all the paths. This figure shows an example of the evolution of traffic flows at a given node or link during a day. We can observe that there are peaks and valleys, that is, time instants, where the flows are relative maxima or minima respectively. First, we will show you how to provide these traffic demand functions, that is, the traffic path flows as a function of time. To define the instantaneous path traffic flows as time functions denoted hp of t, where h is lowercase, we use linear combinations of one or several basic functions with coefficients hpi. To simplify further, we use as basic functions normal density functions, which are defined by its means mu sub ri and the standard deviation sigma ri, as indicated in the formula. This will allow us to reproduce several peak flows very easily and using only a few parameters. We will call demand waves to these waves, one per path. We can better use cumulative traffic flows by means of the hp of t using capital H, that is the cumulative distribution functions, as shown in the formula. The following table gives the normal basic functions used for defining our 9 instantaneous path flow functions, defined by their means and standard deviations, and the corresponding weights or coefficients, hp1 and hp2, where, to simplify, we have used only 2 terms. The corresponding functions are shown in the figure. As you can see, they show a peak in the morning and another one at the afternoon, that reproduce the real behavior of the daily traffic. Once the flows pertaining to different paths enter the network and reach a link, they combine together and produce combined or mixed waves, whose shapes are obtained taking into account the link capacities and the total demand at any time, and provide us with a very useful information. In this animation, you can see how the traffic flow waves deform when traveling along the different links in a given path due to traffic mixing and congestion, and we illustrate how these waves look like. Initially, we have the plot of the path demands as function of the daytime. This means that the network is loaded with traffic entering the path origins at the indicated times. When the traffic reaches the end of the first link between nodes 12 and 6, the initial path wave changes and gets the form indicated on the right plot. Next, when reaching the end of the second link of its paths, node 7, the traffic wave becomes as indicated by the lowest right plot. When the traffic reaches node 11, the traffic wave shows already a congestion trend, motivated by congestion due to different path flows. At the end of the path at node 3, the wave has suffered a new deformation. Finally, here we show the traffic wave at link 711, where we have disaggregated the flows by paths, having a beautiful and useful picture of what it is happening at the node at any instant during the day. In this video, we will explain how the link travel times can be calculated as a function of the actual link flows. In particular, the formulas used to make these calculations will be explained and justified in some detail. This figure illustrates the key idea to establish the traffic balance between two waves, that is, between the traffic flow evolution curves at the path origin and the traffic flow evolution curves at the end of links at a given instant. We use the FIFO rule, which stands for first in, first out, and establishes that there is no overtaking. In other words, any car entering the link before another car exits the same link in the same order. It is very useful to know the departure time of a car exiting a given link A of path P at time t. To this end, we define the function theta AP of t, which gives the corresponding departure time of that car. You can see in the figure two small circles that correspond to the same users at two different locations and times, its departure time and the time the user exits the given link A. The reader should try to understand very clearly the meaning of these functions, because they are key functions in the model. We can evaluate these theta functions in terms of the link traveling times, so that we define the function tau A of t that gives the exit time of a user that enters the link at time t. Then its inverse function ta minus 1 of t out is the entry time of a user that exits link A at time t out. These tau functions are also very important functions. Instead of working with exact inverse tau functions, we will approximate them by monotone cubic splines. The formula relating the theta and the tau function is the one shown here. If we travel back the links of a path P and an is the last link, tau an minus 1 of t gives the entry time to link an, which is the exit time of the previous link in this path. So, using this in the same form to link an minus 1, we obtain its entry time, which is again the exit time of the an minus 2 link. So that, repeating the same process for all path links, we finally reach the path departure time, which is the value of the theta function. In our implementation of this model, we will not use or implement the theta functions because they are a lot. Note that we have the number of paths times the number of links, which is a very large value. Contrary, the number of tau function is only the number of links. However, to evaluate the theta functions, we need to use these formulas every time they are needed. We denote the total flow of path P that has reached the end of link A at time t by EAP of t, a function that can be immediately calculated from the function HP and the theta functions using the FIFO rule. The reader should understand this formula if the meanings of the last two mentioned functions are understood. If we are interested in the flow due to all paths, we just need to add the flows of all paths containing the A link, as indicated in this formula. Similarly, the total flow Rn of t that has reached a given node n at time t can be calculated by adding the flows of all links that have n as its n node as shown in the formula. This formula indicates that the pair of the entry time t and the exit time ta out for link A is used as one of the basic points to build the explain function tau minus 1 of t, used to approximate any entry time of link A associated with its exit time t. To approximate the link travel time curves by monotone cubic splines, we select a discrete set of points, t out of a key, tk, with k equal to 1, 2, and m, where tk is equal to k minus 1 delta, with m equal to 32 divided by delta plus 1, and delta can take different values, for example, delta equal to 0.1, 0.2, 0.5, or 1, if the network congestion wants to be evaluated every 6 minutes, 12 minutes, 30 minutes, or 1 hour, respectively. Next, we explain how to calculate the link travel time. This figure illustrates two users, A and B, and their link entry and exit times tk minus 1 and tk, and tak minus 1 out and tak out, respectively. As you can see, we can calculate the user B link exit time in two ways. First, adding tk and d8 of tk. Second, adding tak minus 1 out and the time qa tk of the users traveling between users A and B to exit this link, as it can be seen in the figure. Then we can write that the exit time of user B is the one in this formula, where we assign as link travel time the maximum of the two values. In fact, we can have more than two expressions to calculate the exit time, and we will assign the maximum of all of them. To calculate qa of tk, since all users in the link xa of tk at time tk exit the link in time da of t, we assign to the users ea of tk minus ea of t k minus 1 between A and B a proportional time to exit the link. That is, if at time t xa of t users require a time da of t to exit the link, then aa of tk minus aa of tk minus 1 users will require a time qa of tk to exit the link. So that, using the proportionality rule, we get the indicated value of qa of tk, and since, under saturation, sa of t is approximately equal to 1 and xa of t is equal to xa x mass, we get the indicated expressions for da of t, which takes as an approximate value alpha a times 1 plus beta a, and then we get the indicated final expression for qa of tk. This justifies the selected formula for qa of tk. After all this process, we have obtained the following equations, which will allow us to solve the problem. Equation 1 provides the path p cumulated number of users at time t in terms of the cumulative normal distributions, where np and n are the number of users of path p and the total number of users, respectively. Equation 2 gives the cumulative number of users of path p at the end of link A and time t, in terms of hp of t and the theta function. Equation 3 gives the cumulative number of users at the end of link A and time t in terms of eap of t. Equation 4 provides the values of the theta function in terms of the tau function of all links in path p. Equation 5 gives the link A travel time ta of t at time t. Equation 6 gives the number of users at time tk inside link A in terms of the eat function, where tk out is the exit time of a user entering the link at time tk. Equation 7 is the BPR travel time function, which gives the link A travel time at time t in terms of the free travel time alpha A, that is, when no other user uses the link, and the congestion parameters beta A and gamma. Equation A defines the degree of saturation SA of t as the fraction of users XA of t inside the link at time t with respect to the saturation occupation XA max. Equation 9 gives the exit time of a user who enters link A at time t of k as the maximum of the two previously mentioned values. Equation 10 gives the value of QA of tk as explained before. Finally, equation 11 provides the cumulative number of users who has passed the end of node n in terms of the EA of t function. Note that the summation is extended to all links whose end node is n. All these equations are time, user or dimensionless equations, as indicated as t, u or 0 respectively in the equations. You can see that we get a system of 11 equations in 11 unknown functions. This is a system of functional equations. It is worth mentioning that we have no derivatives, that is, it is not a system of differential equations. This is because we were careful enough to use cumulative flows instead of instantaneous flows. The advantage is that the solving method is almost trivial, no matter the system be linear or nonlinear. In this system of equations, in addition to unknown functions, we have the parameters alpha A, beta A, and gamma. It is interesting to draw a dependence graph as the one in the figure, where we can see that each unknown function depends directly on other one or more functions, and some of them show a direct dependency on the parameter. The data have been indicated with a thick circumference. We note that the HP of t function could also be considered as a data function, thus the thick circumference in it. You can see that the general flow rotates in the clockwise sense, with the only exception of the functions Rn of t and Ta of t, which are terminal functions. This means that we can initially exclude these two functions and use their corresponding equations to get them once the other functions have been determined. All the above shows that we can use initial spline functions for the functions tau A of t. For example, calculating the free flow link exit time functions and use an iterative method in which we use in sequence all the equations to calculate the same function tau A of t and repeat the process until convergence. This is what we have done in our MATLAB program. In fact, we could also use the functions EA of t, XA of t, SA of t, and DA of t, or the functions theta AP of t or EAP of t, but these two functions are much more in number than the first four. Next, we illustrate all this with some examples. First, we use the illustrative example. The CPU time required to solve the illustrative problem on a portable Dell Latitude E6500 computer was 47 seconds. This figure shows the path flow intensity curves at the different links disaggregated by paths, so that each color corresponds to a unique path. This provides a very useful information about the traffic congestion and travel times. In this form, it is possible to see the combined effect of all of them at each link and the contribution of each path to the total link flow intensity, but it is a bit more difficult to analyze the evolution of each path independently, because both limits are curved lines with the exception of the first path with flow. For the sake of clarifying this aspect, the different path behaviors, in the next figure we can see the evolution of path 6. In this case, the different graphs in the figure show an important distortion due to the congestion produced at link 6, where the link intensity is higher than XA max. More precisely, it maintains its shape, wavelength and height at links 4 and 7 due to the lack of congestion. At link 6, the wave suffers two different processes. One, an elongation due to congestion roughly between 22 and 26 hours, and 2. A wave stretching, wavelength reduction and height increase after 26 hours on, due to the end of congestion produced by the arrival to destinations of users from other paths. The figure shows the link exit time curves as a function of the corresponding path departure times. Since path 6 have 4 links, 4, 7, 6 and 8, we show a set of 5 curves including the path origin curve, that is, the identity function f of t equal to t. These curves provide the exit times of all the links of a user starting the trip at time t, obtained from the link travel time function shown in the upper part of the figure. This figure shows how the traffic wave deforms when traveling takes place along the 4 links, 4, 7, 6 and 8 of path 6. This allows us to calculate the delays due to congestion. In this figure we see the evolution of the different theta ap of t time functions for every path. Each of them permits us to identify the instant at which a traveler reaches the end of every link during the journey. If we pay attention to path 6, it is easy to identify the worst time to start the path travel. In this case, see the figure, the segments T4, T7, T6 and T8 show the time needed for this traveler to cover the different links belonging to this path, links 4, 7, 6 and 8. At the same time, it is interesting to underline that in all graphs the time needed to cover the journey is very similar for people who start at the first and last hours of the day. Our second example is the Nguyen-Dupuy example. In this figure we can see the network associated with the Nguyen-Dupuy example, which has 13 nodes and 38 links. We have considered 60 paths whose details can be seen in the paper. 4 of the assumed path intensity functions are shown in the figure. Note that they consist of linear combinations of 2 normal densities with maxima located at around 8 o'clock in the morning and 15 hours respectively, and different spreads. A complete description of the assumed path flow intensities is given in the paper. We have used the following parameter values: beta A equal to 1 and gamma equal to 3. And the alpha A values have been obtained using a free flow speed of 100 km per hour and the XA max are 100 cars per kilometer. The CPU required time for these calculations on a portable was 544 seconds. Once this path flow has been propagated through the network, we can see the resulting link intensity functions. Some are shown in this figure. Note that they are combinations of the path waves with different delays. The link travel time functions are shown in this figure, where we can see how traffic congestion in the different links varies with time. It is interesting to see the upstream congestion caused by link 14 on links 11 and 35, where induced trends similar to those to the link travel time functions can be observed. The node flow intensity functions appear in this figure, where it can be seen that they are linear combinations of path flows and more complex than link functions, because they involve more paths. Finally, the resulting tau t minus 1 functions after convergence of the iterative process appear in this figure. All these figures have been built with the same criteria as those in the case of our previous and simple example. In this case, due to the high number of paths, 60, only paths 1, 4, 11 and 47 have been considered, but link and node flows show all paths passing throughout of them. It is particularly interesting to see what the evolution of flow corresponding to path 11 is, with important delays in the arrival times as seen in the figure. This path shows a significant evolution of its second wave in links 35, 14 and 18 with an increase of its crest. Finally, we comment the Cuenca network. The 2 examples dealt with in the previous sections were selected with the aim of illustrating the proposed method and showing the corresponding plots of link and node flows, together with the corresponding distributions by paths. In this section, we aim at testing the proposed method with a real network and checking that the computation times are reasonable. With this aim in mind, the methods were applied to the city of Cuenca network with 127 nodes, 672 links, and 219 paths as shown in the figure. We have used the following parameter values: beta A equal to 1 and gamma equal to 1. And the alpha A values have been obtained using a free flow speed of 30 km per hour and the XA max of 100 cars per kilometer. The resulting CPU time was 1215 seconds for the case of no congestion. The observed flow trends corresponding to this example were very similar to those presented before for the small networks. To simplify, we show only a few graphs. In this figure, we have accumulated the link travel times for two paths. The following interesting feature can be observed from this figure. In the case of the path shown in the left graph of this figure, we can see that the first and last few links have no or small congestion, thus showing almost parallel trends. However, some intermediate links have some congestion at peak hours and lead to bands with width changes, leading to a general trend showing relative maxima and minima at peak hours, while an almost horizontal and parallel trend appears in early and late hours in the day. The path of the graph on the right-hand side of the previous figure is composed by link with congestion because this path comes from a very generative zone and goes to a very attractive zone. See that the second last link of this path has a huge increase of link travel time in both peak hours. Again, the traffic is fluid at the early and late hours, showing the typical parallel trend. This figure shows some examples of link flow intensity curves of the Cuenca network with the corresponding path flow components. The difference with previous graph here is that the congestion is almost simultaneous in all links and path flows. Finally, we know that the number of iterations required for convergence varies from a single iteration when there is no saturation at all, reduced traffic flow, to 3 to 12 iterations when large congestion is present. The main conclusions drawn from this paper are the following. 1. Although existing dynamic traffic model based on the hydraulic analogy explain important features of traffic flow, they are very time-consuming and become prohibitive for use in intermediate or large networks. Thus, alternative models become necessary to make them useful in the engineering practice. The proposed method is a continuous method with the link travel time function approximated by monotone spline functions and path origin flow function assumed to be linear combination of normal densities. Both approximations can be improved as much as desired while increasing the set of basic points and the set of basic functions respectively. 3. The proposed method is a possible alternative that implies a reasonable computation time and seems to reproduce real traffic in a sufficiently close way. The path traffic waves propagate throughout the network by stretching and enlarging according to the FIFO rules and the degree of congestion of the corresponding links. The proposed linear combination of normal densities to reproduce the time-varying path flow seems to be a reasonable simplification that is close to the real values. We know that the combination of these functions leads to complex flow intensity evolution curves with a trend similar to the observed curves in reality. 5. The model assumes that the link travel time is a nonlinear function of the link volume and of the immediate downstream path link flows, but some corrections, Q considerations, are made to satisfy the FIFO rule of the basic set using monotone cubic splines. 6. The treatment of traffic congestion is done using an iterative process. We evaluate traffic congestion based on actual link travel time functions which are later updated. The process is started by assuming no congestion in the first iteration. Convergence takes place in no more than 15 iterations when some congestion is present. And 7 and final conclusion, because path flow intensities are used as the basic time functions and the link and node flow intensities are obtained from them based on the network topology, the conservation laws are satisfied over all the networks. Finally, we end by indicating that the computer programs have been implemented in MATLAB without a special optimization effort to reduce the CPU time. Thus, the reported times can substantially be reduced if this optimization, and especially other computer languages such as C, are used. Another alternative consists of using parallel computing, which can easily be implemented. Next, we describe the organigrams or flowcharts that we have used to write the computer program in MATLAB. The input data consists of the network topology, the set of cubic spline basic points, the model parameters, and the maximum allowable saturation and number of iterations, together with the tolerance, to control the convergence of the process. As output, we look for the inverses of the tau functions for all links, because these functions allow us to evaluate anything. In the initiation step, we set the initial values as indicated. In step 1, we check for convergence by means of the tolerance, maximum number of iterations, and maximum saturation. If convergence or out-of-range values are detected, we move to step 11 to end the algorithm. Step 2, 3, and 4 reproduce a nested 3 loop for the basic set of times, all links, and all paths containing the actual link. In step 5, we calculate the departure and associated exit time for link A using the actual spline function as indicated. In step 6, we evaluate the cumulative flows associated with each path using the indicated formula. In step 7, we calculate the number of users in each link at time tk as indicated. In step 8, we calculate the dA of tk values using the given formulas and update maximum saturation times. In step 9, we update the exit basic times for link A. In step 10, we update the splines with the new values of TA out. Finally, in step 11, we stop the algorithm. And this is the end of the video. I hope that you have learned some things to reproduce real traffic by means of a model that is dynamic and is implemented in MATLAB.